My talk is about this recent development on this 3D Navier-Stokes systems. So first we will concentrate on this deterministic Navier-Stokes system. So our model, so the Navier-Stokes equation is written in the following way. So this U in fact is the velocity field and time t and position x. And here we have also this nonlinear term, and this is a diffusion term, and this P is a pressure term. And this nu is the viscosity constant, and this F is the force term. And we also have this nonlinear term and also satisfy this divergence-free condition and also the initial value condition. And such kind of this Navier-Stokes, okay. This Navier-Stokes equation, in fact, can be derived from this Newton's law. So suppose we have the velocity, and so the velocity, in fact, depending on time and the position x, and this position also changes with respect to time. So we have this u, and if we take in the derivative with respect to this velocity, so by the chain rule, we will get this variation term. And we also take the derivative with respect to the x variable. And then by the chain rule, we also take the derivative of this x with respect to time. And then we will get another velocity here. So this is a convection term. So this part, in fact, will equals to the fourth term by the Newton's law. And we will have this internal source and external source. And we also have this diffusion term here. So this is the Navier-Stokes system. And we also assume that the fluid will satisfy this mass conservation, which means its mass is always conserved. So which means it will satisfy this equation. And if rho is a constant, so we will have this divergence-free condition, which means, so this is the usual incompressible Navier-Stokes equation, and also this initial value condition. So this system has first been studied by Euler for the Euler equation, and he considered the case for the diffusions. In fact, this corresponding to this nu equal to 0. So this is the Euler equation. But, and famous Euler equation, and later people found that this when they do some experiment, and this does not match the Euler experiment. So this Euler equation is is just for the ideal fluid, and later and also when this rho number are large. So this, but later Navier and want to understand this viscosity. So he added this term, and also by Stokes, he want to assume this. He assumed this fluid is isotrophic, and then they use this Laplacian term to denote this diffusion term. So later they deduce this Navier-Stokes equations. So this is the derivation from of this Navier-Stokes systems from this Newton's law. And we can, and this can be used for the to model the weather and also the ocean currents and also the water flow in a pipe and air flow around the wing. A lot of things of the fluid dynamics can be modeled by this Navier-Stokes system. And this Navier-Stokes equation can also be derived from the particle systems. So we can see this is like from the microscopic to the macroscopic. So if we consider these particle systems, we have a lot of particle systems in the microscopic sense. And each particles, formally we know that small particles in a fluid behaves like a Brownian motion. So we will have independent Brownian motions, but we also assume each particles have some interactions. So we will have such kind of interaction kernel. So this interaction kernel is given by this Beaver-Savart law. And this BTI is the independent Brownian motion. And we also have this 1/n here. And from here we will see that when n become large and large, so this interaction will become weaker and weaker. So formally, we will see that this xti will become independent. So by the law of large numbers, formally this term will converge to the law of this, to the mean of this k part. So then, so formally we can see that the law of the limiting equation will satisfy the following, the density will satisfy this equation. So we can also check by using the Ito's formula. This impaired Meyer will also converge to this, the law of the limiting equations. So here we will see that this Brown emotions actually give us this diffusion term. So this is another way to explain this diffusion term. And we also have this nonlinear term, which comes from this interaction kernel. So this is this is just the vorticity form of the 2D Navier-Stokes system. So we can see that this Navier-Stokes system can actually be derived from the microscopic to this macroscopic. And also for three-dimensional case, this for more complicated model, this can also be derived by Crostel and Yao for more for the mathematical rigorous result. And in the mathematics result for the, in fact, for the deterministic Navier-Stokes equation, the global existence of weak solutions has been obtained in all dimensions. Here, this weak, we can understand it as some not smooth solution, maybe some rough solutions can be obtained in all dimensions. And the global wilposeness for small initial data. This is has also been studied a lot in the mathematics theory, a lot of people. And, but this is only for the small initial data because of this linearity. And we can also obtain this, but the existence and the smoothness of the solutions in the three-dimensional case remains a big open problem. This is a minimum price problem. So which means that how we can find, so this weak solution is not smooth enough for us to obtain the uniqueness. So how, this is an open problem in this direction. So another direction in the mathematics is that how we can search in singularity, or maybe there is some blow up for the solutions. This has been studied a lot by Terry Stahl and also some other people. And also recently, this is also for this long uniqueness of weak solutions. This is more recently I have some breakthrough work. In fact, for these weak solutions, they can prove there exists for every L2 initial data. There exists at infinite many in solutions, analytical weak solutions. This is more recent results in this direction. So our problem is that can we use this machine learning to understand better for these Navier-Stokes systems? For one direction is that whether we can use this machine learning to help us to find these smooth solutions such that the uniqueness holds. This is one direction. And also another direction is whether we can use this machine learning to find the searching the singularity of this Navier-Stokes system. And also whether we can use this machine learning to compare this different solutions to this Navier-Stokes system. This is our problem. Maybe we can use this machine learning to help us to understand more about this Navier-Stokes system. And now I want to go to this stochastic Navier-Stokes system. So this stochastic Navier-Stokes system this part is the same as the deterministic case. And we also have this external source, so which is given by the Brown emotion part. So this is the noise part. And this, so the motivation for this stochastic perturbation is the following. The first reason is that when we derive such kind of Navier-Stokes system by using the Newton's law, we just ignore some errors, but as we know that, it is known that such kind of errors, when we put it together by the central limit theory, it will converge to the Gaussian distributions. So we use the Brown motions to model this noise term and to see what is the behavior here. So this is the motivation for this Stochastic Navier-Stokes system. So this is for the stochastic reduction. And also this is this Stochastic Navier-Stokes equation is the model of the turbulence. So this turbulence is in fact very is a very natural phenomenon in nature, and people are very want to study the properties of this turbulence, but it is very complicated. So we only hope that we want to study some statistic behaviors of this turbulence. So turbulence, natural hypothesis of this turbulence is the ergodicity result. And I will explain, and when we add in the noise, we can prove some ergodicity result, which I will explain later. And another field is named by this regularization by noise result, which means we add in some noise, the properties of the solutions will become better. So this is some motivations for this Stochastic Navier-Stokes equation. And the mathematics result for the two-dimensional Navier-Stokes equation is the existence and the uniqueness of the probabilistic strong solutions has already been obtained. And the ergodicity result, which means that because we already have the existence and uniqueness of the strong solutions, then which means we can prove that the solution will form a Markov process. So we can study the associated semigroup. And then we can see that this semigroup will finally converge to the corresponding invariant Mayer. And with the convergence rate is exponentially fast. So the ergodicity actually means the time average of these solutions will finally converge to the invariant Mayer of this, will converge to the spatial average of the solutions. So this ergodicity is the usual hypothesis in this turbulence theory. Always the turbulence theory is working under the law of this invariant Mayer. And also more recently, there's some progress in this direction. They can prove mathematically about this battle spectrum result for the two-dimensional Navier-Stokes equation coupled with linear equations. So this is some mathematical rigorous result for this turbulence. And for the three-dimensional case, there's only martingale solutions because we don't have the uniqueness result. So there's only martingale solutions. But as there is no uniqueness result, so we cannot directly say that the solution is a Markov process. So, but we can try to find the Markov solutions. So we can do the Markov selections here. And we can also obtain the ergodicity for the non-degenerate when the noise is, we have enough noise. And we also have this, for the small initial data, we can also obtain the global well-posedness result. But recently, we can also study this non-uniqueness result for the three-dimensional Navier-Stokes equation. And we can prove that the non-uniqueness in law holds in this case. And we can also prove that there exists a global probabilistic strong solutions in this sense. Because usually we need the pathwise uniqueness to deduce this. But now we can use this new method to obtain this existence and the non-uniqueness of this global probabilistic strong solutions. And moreover, we can also obtain the Markov solutions. We can construct the more Markov solutions. So we can in fact prove the non-uniqueness of Markov solutions. So this is recent progress in this three-dimensional case for this Stochastic Navier-Stokes equations. Our problem is that how about this non-uniqueness of the invariant Meyer? So whether we can use this deep learning to understand the long-time behavior of this, as we already have this non-uniqueness result. Whether we can already obtain the non-uniqueness of the invariant Meyer. So this means whether we can find, how about we can find two egodicity Meyers, or for this Navier-Stokes systems, and to see the different long-time behaviors of these Navier-Stokes systems. Whether this deep learning can help us to modeling this result. So from a mathematical point of view, this is unknown to us. We still cannot obtain such kind of result. Maybe this deep learning can give us some hint or some insight for this direction. And also, I want to mention some open problems in this related to this turbulence. So this turbulence is usually people model the turbulence is by such kind of Navier-Stokes systems with a force. So such force is usually driven or some noise term, and there are there are some predictions for the turbulence by some laws, from statistical laws. And the first one is the famous one is by Kolmogorov, and for this zeroth law of turbulence, which means this when this viscosity constant goes to zero, so this corresponding this energy term. In fact, the limit will not equal to zero, but bigger than zero. This has been, so this integration is with respect to the space variable and also the stationary Meyer. And we have such kind of stuff, and this can be proved, has been predicted by Kolmogorov and also checked by a lot of experiments. But whether we can use some deep learning to understand more of this statistical law of this turbulence, and also in this turbulence of this Kolmogorov theory, he defined some such kind of piece order structure function, and also he predicts that this one. As this nu goes to zero, and this one will behave like this part. And also have such kind of zeta p which should equal to p over 3. But this result, by experiment, they see that this p is equal to, when p equal to 3. So this should be true, but when this p is bigger than 3 or smaller than 3, there should be some deviations for such kind of theory. So whether this deep learning can help us to understand of this law, and whether we can get some exact value of this zeta p. This is what we hope to understand. And also of this famous, this 4 over 5 law, and also this is held in this when nu goes to 0. And that's all, thank you.